So a week or so on from the Education Estates event in Manchester, I just wanted to share my thoughts on a panel session that I was involved with, discussing the topic: Are heat pumps the answer? And particularly in the context of decarbonising heat in schools. And the point was really put to the audience that, firstly, heat pumps, although a low carbon technology and well established, actually their application in existing buildings is causing some problems. And actually, the fact that this is almost becoming a mandated technology now sounds like more of a decision than a strategy. And the point of this panel session was to discuss this very topic. Actually, are heat pumps the right solution to be putting forward, particularly in renovation schools projects? So this is my point of view on this particular topic. I had about a 10-minute session to explain this. I'm going to try and run through this a bit quicker in this particular recording. And I spoke alongside some representatives from Cundall and also from Arcadis as well. And my response to the question posed, are heat pumps the answer, actually is yes, I believe they are. Heat pumps are an established technology. Those of you who know me will know that I've been involved in the heat pump sector for many years before my time at Hysoft. But actually, there's a caveat to all that insofar that they are the right technology if it's applied correctly and appropriately. And sadly, we see the misapplication of the technology in many instances. So, in fact, my response to that question really is not are heat pumps the right solution, but actually is the current approach we have to heat pump design actually working? And I would argue that is the issue rather than the technology itself. What I would say is that heat pumps are not a like-for-like replacement for gas boilers. I think that's obvious. What we mean by that is you can't just remove a gas boiler and plonk a heat pump in its place. You need to look at the application and the whole system designed correctly. And we hear a lot of preconceptions in the market about heat pumps are not suitable for existing buildings because of operational temperatures. They're cost prohibitive. You have to replace all the radiators. You have to use high temperature units, are the only thing that's suitable for renovation projects. Or that significant cost increases are inevitable in terms of operational costs because of the cost difference between gas and electricity. And these things can and often are true, but they don't need to be, particularly if you take the proper approach to system design and you consider all of the aspects of the system rather than just replacing the heat generation asset or one heat generation asset with another. And in fact, the evidence is that systems are not being applied as well as they should be. This is a short extract from the Salix PSDS Phase 3A summary report, and shockingly, what it's showing is that of the 248 heat pump installations that were funded under PSDS Phase 3A, only about 15% of them were optimized. Less than 30% included heat distribution system upgrades, and less than a third had BMS upgrades. And what leads to are performance gaps between what people expect these systems to do in theory and on paper and what they end up getting in real life. That's predominantly due to the overestimations of heat pump system performance and without taking that whole system approach to design. So here's an example of this. This is a project we worked on with Newcastle City Council under one of the first phases of PSDS. It's quite a large system, and the idea here was to replace the existing gas boilers with heat pumps. Just as a benchmark for that system, the running cost of gas of that installation was about £28,000 per year. Now, this is the original design proposal. We see this all the time, where this is a like for like. Take the boilers out, put heat pumps in. And what we see here is a system that ends up being significantly oversized. We can see here that the real heat demand of that building was only about 650 kilowatts, and yet the proposal is to put nearly a megawatt of heat pumps in. High temperature units, not changing any of the radiators. It was assumed that system, based on manufacturer's data, would have a seasonal efficiency of about 3.2. We know from modelling and simulating, and I'll explain more on that in a minute, that installation in a digital twin, that system would only have ever operated at a seasonal efficiency of about 1.8. So that would have had a huge detrimental impact on the operational energy costs, more than doubling them. It would have limited the amount of carbon savings can be made, and actually the capital cost of covering the whole heat demand with heat pumps was actually quite significant. Fast forward a bit, and we look at actually how when we take an approach where we're optimizing the whole system, looking at the distribution systems, the hydraulic issues, the control issues, and actually applying this technology in a more holistic way, what we can end up with here is a hybrid solution where we're able to use low temperature heat pumps, haven't changed any of the radiators. We're able to run them on the existing radiators at low temperatures, less than 50 degrees. We only need a 300 kilowatt heat pump, and we can see that heat pump still doing 98% of the annual heating demand, running at much higher efficiencies. We can see that it delivers much higher carbon savings. The fact it's a hybrid system and only 300 kilowatts means the capital investment costs are much lower, and actually the impacts on energy costs for that school are much lower as well. So a much more viable system for that particular application. And those of you that know Hydrostopt, you're on this video, so I assume you know a bit about Hydrostopt already. But we know all this by being able to use our digital twin design, simulation, and optimization software to be able to model that installation in the virtual environment, understand the impacts of optimizing the distribution systems first, use the oversizing in that system to our advantage to run at lower temperatures, optimize the control strategy so we're not having peaks in the morning but actually having a much more consistent level of heat through the day. That enables us to go from that megawatt of high temperature heat pumps to only 300 kilowatts of low temperature heat pumps, and we can prove that will work in the digital model before we go and actually apply it in real life. Here's another example. This is a college that we've been working with recently in the north of England, where they had an existing heat pump installation installed, again under early phases of PSDS. It's actually quite a complex system with heating and cooling in it as well. But by modelling their installation after a year of its actual operation, what we were able to find was significant performance gaps in between the way the system was actually operating now and how it could be operating if it's optimized a little further. The client in this instance is very happy. They've already reduced their gas consumption by around 45%. But what we were able to show them is by optimizing that installation further, there's another 34% gas consumption reductions that could be made, and another 23% carbon emissions that could be saved just by optimizing what they already had. Essentially, the system's boiler led, and once the temperatures outside dropped to about 5 degrees, the heat pumps would effectively be switched off and the boilers were doing all the work. So actually we can improve that situation by optimizing that system, and we prove that in the digital twin, and we then go and apply those changes in real life. Now that has two impacts for the client. It means their carbon savings can be increased, which is great, but also it actually meant, sadly, that they ended up having to spend more of their own capital to top up the PSDS grant originally than they needed to, because those carbon savings were left on the table. So important to look at these things earlier in a project if you possibly can. So that's a very quick run through all of this. What I would say, in conclusion, that heat pumps are great technology. They work well, they're proven technology, but they're not a like-for-like replacement for boilers, and you really shouldn't consider them to be so. It's really important to apply the technology correctly, and that means taking a whole system approach to the design. It's not just about removing the heat generation and changing one plant type for another. To optimize the best performance, you need to understand the full system hydraulics and the full control strategy and how all that works together as a system rather than just individual elements or components. And what we're finding is, the current approach to design, tools that are being used and practices are falling short of what's needed to allow this technology to actually flourish. And thirdly, it was a theme throughout the talk, not just my comments, but also the other speakers were saying that really that hybrid systems make a lot more sense. And although hybrids with gas boilers aren't permitted anymore under PSDS, there are other routes, by the way, to putting these sort of systems in. Even using direct electric backup to cover some of the peak loads makes a far more capital cost effective approach than trying to cover the whole heat load with heat pumps alone. But to do that, you need to understand the trade-offs between the operational costs, the capital costs, and the carbon savings. And the way to do that is using a technology like a hydraulic system digital twin. If that's all of interest to you, we have a whole white paper on this whole topic, which you can download from our website. Hope that was useful, and thanks for listening.